I wanted to put together a short video about extreme values of functions in Calculus 1. So these are single variable functions. First off, some terminology here. So say we have this function f of x, and there's a lot of things going on. What we're interested in is the highs and lows of the function. And so what we see here, this seems to be important. This is what ends up being called a local maximum, whereas, and this is sometimes called a relative maximum as well. Different books will use different sets of terminology. Down here, this sort of valley seems to be a minimum, so it's what we'll call local minimum. And then there's other things that are happening here, but those are really the key features. These are the highs and lows, the peaks and valleys. And so one of the first things you got to recognize is the difference between what are called local maxima, relative maxima, and global maxima, or absolute. And so an absolute maximum, or an absolute extreme value of f of x would be a value where some value f of c which is larger than f of x for all other x's, or smaller than in the case of a minimum for all other x's. Or equal, I mean, since it's greater than or equal to, we're allowing ties. So if you have two bumps that have the same height, for example, whatever that height is, it's the f of c that is really the height. It is the best time, not the person who got the best time in a race. It is the height of the peak and not the coordinates of the peak. And I will say that varies from book to book, different treatments of this subject. Sometimes it's the input that is considered the absolute extreme. Sometimes it is the output that is considered the absolute extreme. And so you want to know, do you want the x or the y value? And the book should specify, or your instructor should specify. So these are the absolute extreme values, this idea for all x values. The local or the relative extremes, if I were to say, turn this into local extreme values, there's this somewhat vague notion, admittedly, of f of c is greater than f of x for all x nearby, or for all nearby x values, and likewise for the minimum as well for all nearby. Because if you look at this minimum, for example, at 2, the function gets lower. It just doesn't get lower nearby. And so if you want to formalize this, you start looking at the idea of there is a neighborhood, there is some interval around 2 for which this is the smallest, or in the case over here, there is some interval in which that is the largest. There is some window that you can restrict yourself to. So it is the largest in its neighborhood rather than the largest in the world. So for this function, this has local extremes. This actually has no absolute extremes in the general sense. That if this function were to continue down to the left here and up to the right, there is no absolute maximum, there is no absolute minimum, because no matter what number you try to claim is the absolute maximum, the function always gets bigger than that. Whereas if we had a function that did maybe, say, like something like x squared, just to keep a simple case, that height of 0 is your minimum, and it's a local minimum, and it's actually an absolute minimum as well, because nothing gets lower than that. And you can imagine sine of x, for example, has an absolute maximum at 1 and an absolute minimum at -1 forever. And if we took this curve and we chopped it up, if we said, oh, we're only interested in this function from -1 to 3, for example, then the absolute maximum within that, then you start messing with all x value. You mess with the meaning of all x values in the interval you're interested in. So the absolute maximum value of f of x on, let's say, -1 to 3 is this height at, it looks like that's the highest point, at 1. So the absolute maximum value is 20, which you could say happens at x equals 1 if you want to specify all details. And the absolute minimum for f of x on that same interval is looking through here. It looks like it doesn't get any lower than 0, which is that x equals -1. So for a picture, this is fairly easy to spot. You just look for how high does it get, how low does it get, and that's long and short of it. If you're just given an algebraic expression, though, we need some tools to really analyze that. And that's where a lot of the work happens in a calculus class. So we want to know, where can these extremes happen, whether they're local or absolute, where can they happen? First off, if we look at where these absolute extremes happened, the maximum happened here at one of these, at a place that also happened to be the local maximum, whereas the minimum happened at an endpoint. And the good news is, those are the only two possibilities. An absolute extreme, I'll put this over here, an absolute extreme on an interval, on a closed interval from A to B, happens at either the local extreme of the same type, maxes happen at maxes, or endpoints, and only there, which narrows our list of candidates for where we have to check for how high things are down to a pretty narrow category. We really only have to check that endpoint, that local min, and that local max and that local min. And one of those four is guaranteed to be the absolute max, and one of those is going to be the absolute min, assuming continuity. If you've got breaks, if you've got jumps, you've got asymptotes, all bets are off. You may not have absolute extremes in those cases. 1 over x, that curve does not have absolute maxes or mins because it goes up and down indefinitely. It's just like this one does, except this happens in the middle. All right, so we've now narrowed our candidate list down to endpoints and local extremes, but we just traded one problem for another. How do we find these local extremes? That's what Fermat's theorem does. So Fermat's theorem is all about where can these local extremes occur? And it comes down to just a few places. A local extreme for f can only exist at x equals c at a certain x value if either the derivative is 0 or the derivative is undefined. Those of you with some previous exposure to calculus may recognize these two conditions as something called a critical number. Now this is a definition that can vary book to book. Sometimes they call them critical values, sometimes they call them critical points. I'm going to go with critical number. It's really about an input. And so formally, what a lot of textbooks define, especially Stewart, is that x equals c is a critical number. So that c is a critical number for a function f of x. For f of x, if, and then there's three conditions. And sometimes these get tucked away inside of the way the definition is phrased, but I'm going to lay them out like a checklist. First off, you need f of c to be defined. A lot of times they say a number c in the domain of f. So c is in the domain of f. But that is a kind of technical condition, which doesn't show up here, but it is something you have to check independently. And then the other two are based on these conditions. F prime of c equals 0, or f prime of c is undefined, and this is an or. So those two are, you need one of those two, and you need both that and one of those two. And so, for example, if we had a function like f of x equals x over x minus 1, this function is undefined at x equals 1. But if we go take the derivative, f prime of x, I can do some chain rule, bottom times the derivative of the top minus top times the derivative of the bottom, all over bottom squared. It sounds like this, that you want to not really have to think about quotient rule. You want to just be able to do it. This is why it's worth drilling a little bit just to make sure you have everything solid so you don't have to think too hard. X minus 1 squared, and so that's going to be -1 over x minus 1 squared. That's our f prime. This is never 0. This is never going to be 0 because that numerator is never going to be 0. It's always going to be -1. And the denominator, when you have it written like this, is really nice because you can find out when f prime is 0 based on the numerator. You can find out when f prime is negative based on the denominator. So that x minus 1, it's actually undefined. F prime is undefined at x equals 1. Now, this seems to check off this f prime is undefined box, except that the original function is not defined either. So technically, 1 is not a critical number, technically, according to the definition, but it is still important. It is where an asymptote happens. It is where potentially increasing and decreasing could change. So when you're later on in the course, when you're looking at is the function increasing or decreasing, you're going to need to check on both sides of 1. It's quite possible that the increasing, decreasing behavior changes. It doesn't for this one. It's always going to be negative because of the example. But in general, it could change at that number that's not really a critical number, but it's still important. It's a bit of an arbitrary definition, but it's useful in places. So, and by the way, in this case, there is no critical number at all, because there's 1 is the only thing that was possible, and it doesn't actually count. And so once we have Fermat's theorem, that tells us where local extremes might happen. It actually doesn't tell us once you find them that they definitely are. It's another thing that I should mention, getting ahead of myself with that paper. Critical numbers are potential extremes. Where can local extremes occur? It's not where they must occur. You can have all sorts of fake outs. So for example, if I've got a function like this, this, for example, I actually saw this in the other one. For something like that, we've got the derivative undefined here, and it also happens to be a minimum. Here the derivative is 0, and it happens to be a maximum. Here the derivative is 0, but it's not a maximum or a minimum. It just happens to be a horizontal tangent line. In Calc 3, these are sometimes called saddle points. The idea is that you can sit on it, I guess. It makes more sense in 3 dimensions. It looks more like a saddle in that case. But it is entirely possible that you have a 0 derivative that is not a maximum or minimum. You can also sometimes call this a stall. Like things stall out. The rise happens, pauses, and then keeps going. A stall or a pause. And I guess there's one last instance of what might happen. You could have a vertical tangent line. And in that case, you have the derivative as undefined, but that's not a maximum. It keeps growing. And so you'll see stuff like this happening for y equals x cubed has that. Y equals x cubed looks like that, or really x to any large odd power. Cube roots will do the opposite, and y equals x to the 1/3 or 1/5, the 5th root will have this vertical tangent line versus the horizontal tangent line. Whereas these peaks and valleys, those can happen at y equals x squared or any even power, and those sorts of actual minima at undefined derivatives happen at things like x to the 2/3. That's something that will induce that. And it's x to the even over odd. We'll tend to do that 4/5, 6/11 would have this kind of pointiness to them. Also absolute value. Absolute value will also do that. It'll be a minimum without being a derivative being there. All right. Well, running a bit long on time, so I'm going to cut the video here, and I'll do a part 2 with that closed interval method sheet you saw before.